Well, ladies and gentlemen, good evening. My name is David Jamieson and I'm the organiser of the July Lectures in Physics program. It's my great pleasure tonight to welcome you to the fourth and final July lecture in our series. Those of you who have been here for the previous three will know that the year 2005, next year, has been declared the International Year of Physics by the General Assembly of the United Nations. And that is because it's the 100th anniversary of Einstein's miraculous year of 1905. So we anticipate a very big year next year for physics, and the federal government, our science minister has very kindly offered us some funding for a major program of physics activities next year, to which I would invite you all once we decide what we're going to do. But this year, on the 99th anniversary of Einstein's miraculous year, we thought it was appropriate to look at physics before Einstein. And we've done that in three key areas already over the previous 3 Fridays. And we're going to wrap up physics before Einstein with the topic of the ultraviolet catastrophe, so-called, which was one of the most puzzling aspects of a puzzling result in physics of the late 19th century that Einstein explained. Tonight's speaker, Professor Ray Volkas, is one of Australia's most distinguished theoretical physicists. His work attracts enormous attention and respect, and in fact over his career his research publications have been cited more than 1,800 times by other scientists worldwide, which is truly a remarkable record. So I give you Professor Volkas.
Thank you, David. And thank you all for coming on this dark and stormy night. I know it's very cold out there. Hopefully this topic will warm you all up. So I'm going to be talking about the red-hot emergence of quantum mechanics from something called the ultraviolet catastrophe. Now, what I'm going to do is first of all describe the general kind of intellectual background that you need in order to appreciate what the catastrophe was, and then eventually how the solution to that catastrophe actually led to the formulation, or the beginnings of the formulation of quantum mechanics. Now the problem is as it arose at the end of the 19th century, came from trying to understand something very, very mundane, and that was just how do hot objects glow. Now, you know, we like hot objects. We use them for cooking. We use them for radiators. We're hot objects ourselves. We emit radiation. This is a very commonplace kind of circumstance that objects emit radiation. And so to really understand the world, you want to understand exactly how it is that radiation is emitted by hot bodies and what is the character of this radiation. And this involves two separate kind of sub-disciplines within classical physics, within 19th century physics. One of them is thermodynamics, which is, as the name suggests, the physics of heat and so on, temperature. And the other is electromagnetism, and particularly classical electromagnetism, that is before quantum mechanics came in, because the radiation that is of course emitted by hot bodies is electromagnetic in nature, of which light is an example and infrared is another example. I'll have more to say about that as we go along. But to understand how the character of the radiation that was emitted by hot bodies, you needed both thermodynamics and theory of electromagnetism. You have to put the two together and try to understand this rather mundane, apparently mundane problem. And the problem was that when you did this, and some very, very intelligent people tried to do this, they got complete nonsense. They got something called the ultraviolet catastrophe, and I'll describe what that is. But in short, they predicted that an object should emit an infinite amount of energy at extremely high frequencies. And this doesn't happen. We don't all glow in gamma rays, for example, and that's basically what they predicted. So it was obviously wrong, but the problem was that there was nothing wrong with their reasoning. If they took thermodynamics, as was well established for a couple hundred years, and they took classical electromagnetism, which had a number of triumphs and was obviously in many ways a correct theory, and put them together, they got something that was nonsensical. So that was the problem, in short. Now, I'm going to describe a little bit both about thermodynamics and electromagnetism, these two different theories, and then talk about how various people try to combine them to understand the radiation from hot bodies. And I found this, the web is a wonderful thing, and now you can find all sorts of stuff without really trying. And I found this wonderful quote. This is from a biography of a famous thermodynamicist, an American thermodynamicist called Gibbs. It was actually written by one of his students, published around 1951, I think, by Yale University Press. And anyway, it says, "The history of thermodynamics has always seemed to me to be not only one of the most interesting, but one of the most dramatic episodes to be found in the story of the intellectual progress of the human mind. Starting in an investigation of a purely practical problem of something rather grungy, engineering economics, it has grown into a body of doctrine of profound philosophical significance with consequences which permeate the thinking of men." We were back in 1951, all right? Men on many subjects, from those with the most practical use to the problems of cosmology. So apparently from thinking in depth about this sort of mundane stuff, all sorts of profound thoughts are elicited, and somehow the process that you go through, the things you need to understand these mundane things, actually have consequences that are more far-reaching than you ever imagined. And this is actually true. I mean, thermodynamics is extremely important, for example, in cosmology, and I'll touch on that right at the end of the lecture. Now, it just so happens that when I was eating my breakfast this morning, I turned to page 6 or whatever it was of The Age and found this story. Now, maybe many of you have been following this in the papers the last 2 or 3 days. Stephen Hawking, probably the world's most famous physicist, about 2 days ago recanted a view he held concerning the behavior of black holes. Probably only those of you in the very front rows can actually read this article, so let me just quote a little bit from it. "He has stunned the astrophysics community with a backflip on his pet subject of black holes." Now, why am I introducing black holes here? I'm going to be talking about hot bodies and so on. Let me explain. So, what did he recant upon? Now, you know that black holes are famously regions of space-time with such a strong gravitational field that when objects fall into them, they can never get out, and in fact, light itself can't get out, and that's why these things are black. And therefore, these things sort of act as a sort of universal gobbler of things. And what you get after this black hole has eaten something is just a slightly bigger black hole. So the idea is that this particular kind of entity, a black hole, actually destroys information. So for example, if you threw the collected works of William Shakespeare or Isaac Newton into a black hole, all of that information would disappear forever. It would appear. And this loss of information, this irretrievable loss of information inside a black hole has been considered as a troubling feature to some physicists. But Hawking has been famously arguing for about 20 years that this loss of information is truly there. It is real. Black holes destroy information literally. And that is the belief that he has just recanted on 2 days ago. Now, what has this got to do with thermodynamics and hot bodies and so on? Hawking came to fame early in his career for theoretically discovering something called Hawking radiation. What he actually found was that a black hole is not exactly black. It actually does emit a form of radiation. This is ordinary electromagnetic radiation and other kinds of particles as well. And it just so happens that the character of the radiation, which is now called Hawking radiation, emitted by a black hole, is essentially identical to the radiation emitted by an object that I'll talk about a lot here, which is called a black body. Now, a black body is a kind of idealized, everyday lump of stuff. And I'll tell you exactly what it is later on, and we'll have a few demonstrations to illustrate it. So a black hole, amazingly, glows in exactly the same way that an ordinary object glows. And the point is that a black hole absorbs anything that falls into it, destroys the information, and then re-emits radiation. And the question is, does the information that was apparently destroyed by the black hole, reappear when the black hole subsequently emits this radiation? And Hawking had been arguing for 20 years that in fact you don't get the information back because the character of this radiation is very, very bland. It's something that we physicists call thermal radiation. It's infinitely bland. All the information has been kind of all averaged out, and you don't get anything much in the way of useful stuff out of this Hawking radiation, which is very much like the radiation from ordinary objects. So I just thought it was interesting to throw this in, since we're talking about blackbody radiation here in the ultraviolet catastrophe. This is just an example of how apparently mundane physics actually reappears in a completely different context. In this case, these very exotic objects called black holes. Anyway, unfortunately for Professor Hawking, he made a bet some time ago with a guy at Caltech, John Preskill, that in fact information is definitely destroyed, and Preskill said, no, the information is retained in a black hole, we just haven't been clever enough to work out how to access that information. And now that Hawking has recanted, he's had to pay up his debt, and the debt, you can't read it, but Professor Preskill will receive an encyclopedia on baseball. Okay, so I guess he's a happy guy. And I just leave this up for a moment's reflection. If you want to know the technical background to exactly what made Hawking recant, please feel free to cogitate upon that. Okay, now back to thermodynamics. Now, thermodynamics is an old subject. It really got going in the early 18th century with the advent of the Industrial Revolution. And in fact, it's interesting that the history of this subject of physics, thermodynamics, is intimately tied up with a major movement in history, the Industrial Revolution. And in particular, Newcomen and also Watt, with their developments on the steam engine, and really trying to understand the steam engine, which was the powerhouse of the economy during the Industrial Revolution, required the development of the intellectual subject of thermodynamics. So this is the engineering economics that the previous quote is really referring to. So anyway, this is just a very, very brief history of thermodynamics, starting with the Greeks, of course. The Greeks started everything, and then various things along the way. The major thing really being the study of engines of one sort or another, and the Industrial Revolution. Eventually, thermodynamics was codified in a set of basic principles, which we call laws. There's the first law, just says that energy can neither be created nor destroyed. It just gets turned from one form into another. There's another one called the second law, which is the law of increase of entropy. This says basically that if you put a hot body next to a cold body, heat will flow from the hot body into the cold body until they are at equal temperatures. And you would never find that the hot body gets hotter and the cold body gets colder. So it represents a directionality in thermodynamic processes. In around about 1861, a guy called Kirchhoff defined this notion of a black body, which I'll talk about a lot during this presentation. And also another thing that was a hot topic during the 19th century was the atomic basis of thermodynamics and concepts like heat and temperature. You can think of the physics of something like a steam engine in many ways without introducing an atomic view of what's going on. And so there was a debate about whether an atomic view was essential. Did atoms really exist? Which was a topic of another July lecture this year. And anyway, of course, as you know, atoms do exist, and so eventually it became clear that to really understand thermodynamics properly, one needed to look at the microscopic constituents of everyday objects and see how they moved and how they kind of jiggled about. And what I'm going to really focus on here is an event that occurred in 1900, which is when a guy called Max Planck, a German physicist, introduced the idea of the quantum in very, very primordial form. This was the tip of the iceberg, and from this flowed the whole very sophisticated theory of quantum mechanics that we have today. And he introduced this in order to understand the properties of hot bodies, and he ushered in modern physics. So physics, as you may know, is divided into kind of two epochs, before 1900 and after 1900. Before 1900 is classical physics, particularly before quantum mechanics, to a certain extent also before relativity, another of Einstein's contributions, which we'll talk more about next year. But especially the physics before the quantum was ever thought of is called classical, and everything after that is modern physics. Okay, so thermodynamics is taking this atomic point of view, which I think is really helpful in terms of visualizing what's going on. If you think about a gas, for example, say the air in this room, the air in this room consists of a whole lot of zillions and zillions of molecules and atoms, and these molecules and atoms are moving in all sorts of possible ways, sort of chaotically within this room, in a very disordered kind of motion. So to work out the motion of any particular atom in the air in this room is an impossible task. But if you look at the physics of the air in this room as a whole, then we can talk about that. We can do physics with it, we can calculate with it, we can understand how it works. So it's kind of the sum total of the disordered motion of all of the atomic constituents of ordinary matter that is really the topic that is covered under the rubric of thermodynamics. And this doesn't just involve gases, but also liquids, solids, basically everything, even black holes. So the kind of key concepts are things like heat, temperature, pressure, and entropy. So I'll be talking a lot about temperature. So I wanted to just refresh your memories about exactly what temperature is. Now, what this sort of cartoon depicts is a gas, which is encased in some sort of a container. And these little black things here are meant to be atoms of various different kinds moving around in this disordered way in this gas. So this one's moving that way, this one's moving that way, they're moving in all sorts of directions. And one of the properties of motion that will be very important, that is very important, is kinetic energy. It is how much energy is carried by a mass that is moving with a certain speed v. And as you may remember from high school physics or wherever, the kinetic energy of a moving particle is given by this simple formula. You just take the mass of the particle, multiply it by the square of its speed, multiply by a half, and that is something called kinetic energy, which is a very, very important concept. Now, in a gas, all these zillions of particles in the gas each have a kinetic energy, but the motion is very, very disordered. And temperature is basically a measure of the average kinetic energy of this disordered motion of atoms in a gas or a solid or a liquid. So I'm going to show you very few formulas, but this is one I really sort of have to. All this says is that the average kinetic energy of a molecule in a gas is proportional to its temperature. So the hotter a substance is, the more quickly the atoms in that substance are moving. And the kinetic energy is directly proportional to the temperature. There's this constant here called K, which will appear all over the place. It's a bit of a nuisance. It's called Boltzmann's constant. Don't worry about it too much. The only thing that Boltzmann's constant does is basically to convert Celsius into joules. You know, joules is a measure of energy, and Celsius is, or a degree, is a measure of temperature, and all K does is really convert from temperature into energy units. So just ignore K and just think of the right-hand side here as T. Now there's this other factor here, which is 3 divided by 2, 1.5. And we need to examine that a little bit more in order to understand actually how the ultraviolet catastrophe occurred. So I just want to highlight that little 3 there. And that is a very important 3 for us, and we're going to become obsessed by this 3 for the next few minutes. Okay, and the other thing I should say about temperature, I've already briefly mentioned it. When you bring 2 objects together which have different temperatures, what happens is that they, what we call thermally equilibrate. Heat flows from the hot body into the cold body until the temperatures are the same for the 2. And we call that a state of thermal equilibrium. And the 2 objects are then at the same temperature. And in fact, when you put a thermometer in something, what you're doing is causing the thermometer to come into thermal equilibrium with whatever substance you're trying to measure the temperature of. And then when they are in thermal equilibrium, you can just read the dial on the thermometer, and that also tells you the temperature of your body, or whatever it is you're measuring the temperature of. Okay, now there's one hard part to this lecture. It's a little bit technical, and it has a very, very boring name. It's something called the equipartition theorem. Forget about the name. I just want to give you a feeling for what this concept is, because it's really central to understanding why classical physics just completely failed to explain this very important aspect of the real world, the radiation of hot bodies. One other technical thing I have to introduce, and this is about the end of it, not quite almost, is this idea called a degree of freedom. A degree of freedom is a technical term in physics which tells us how many independent ways a body can move. And I want to just illustrate that with a very simple example. So consider just a particle, you know, just an atom or something like that. So there it is. An atom is a little bit smaller than that, but it looks roughly like that. Same color too. And one feature of an atom is that it can move in 3 independent directions. It can move in the direction X, it can move in the direction Y, and it can move in the direction Z. And you're meant to think of these X, Y, and Z arrows as existing in 3-dimensional space, like my fingers, like that. So a point particle can move in 3 independent ways because there are 3 dimensions in space. All right? And so we say that a free particle, well, so there is a statement that a free particle can move in 3 independent directions, and we call we therefore say that a free particle exhibits 3 degrees of freedom. There are 3 independent ways that it can possibly move. So this is just an abstract idea, but it's a fairly simple one, and it will be important later on. Now, suppose instead of a single particle, we actually now have a gas of many, many particles, many atoms. We need to answer the question, how many degrees of freedom does that gas have? How many independent ways can the atoms in that gas move? And the answer to that question is actually very, very simple. What you do is you just take the number of atoms that you have inside your gas. Each of them is a point particle, and each of them can move in 3 independent directions, X, Y, and Z, for that particle. And then if you have zillions, you know, if you have capital N atoms in your gas, and N is a zillion or something like that, you just multiply 3, which is the number of different ways that a single atom can move, by the number of atoms that you've got, and that tells you all of the degrees of freedom of the whole gas. This is the number of independent ways that the atoms in the gas can move. And this will be a huge number, of course, an absolutely huge number, but something that is very simple to calculate once you know how many atoms you have in your gas. And this 3 is exactly the same 3 that we saw on the previous slide. And this horrible thing, the equipartition theorem, says the following. If you want to know how much energy an ordinary system has, like a gas or a solid or something like that, one way to calculate it is to just work out how many atoms you have inside your gas. You know that each atom can move in 3 independent directions, so the degrees of freedom is equal to 3. You multiply 3 by the number of atoms that you have, and then the key thing, which I won't explain but was implicit in the formula on the previous slide, was that you multiply basically by the temperature divided by 2. And the multiplication of those quantities tells you the total energy of your gas. So there are a number of concepts that come into this. The total number of particles in your gas, how many independent ways each particle can move, and then the fact that on average each particle contributes basically the temperature divided by 2 to the total energy of the gas. Okay? So once again, I'm just trying to underline the fact that temperature is a measure of how much movement atoms are having in a gas, how much kinetic energy they have on average. Okay, so try to remember that. This is the hardest thing I'll do, I hope. Okay, now, so far I've been talking about particles, but electromagnetic radiation exists in the form of waves, and there's a lot of evidence for that electromagnetic radiation is wave-like. Interference experiments, all sorts of things. Electromagnetic radiation behaves in many respects exactly like water waves. It's a wave-like phenomenon. So, if we want to understand the electromagnetic radiation given off by a hot body, we have to know how to do the thermodynamics of waves. And this is something completely different. A wave is an extended, fuzzy thing. It's not like a point particle. So how is it that we can generalize notions like temperature and energy and so on to develop a way of thinking about what we might mean by a thermodynamics of waves, which is what we have to do if we want to understand how a hot object, which has lots of atoms jiggling around in it, actually emits electromagnetic radiation. And what we're going to do is follow these two guys, Lord Rayleigh and James Jeans, and we have to use this equipartition theorem in order to work out this sort of mysterious thing, the thermodynamics of waves. But before doing that, I should say a few words about electromagnetic waves themselves. So, introduce another character in the story, James Clerk Maxwell. Didn't have an extremely long life, but a very, very productive one. And he wrote down the fully complete mathematical theory for electromagnetic waves. He described how electric charges interact with electromagnetic waves, and there were a lot of triumphs of this theory, and it is still the theory that is used today when you can ignore quantum effects. Okay? So it describes electric fields, magnetic fields, electromagnetic fields like light and radio waves, and how these things interact with charged particles inside atoms like electrons and protons. So one of the great achievements in the late 19th century was just to prove that light was a form of electromagnetic radiation. This wasn't at all obvious. And Maxwell's theory allowed this proof to occur. And so what I've depicted here is the electromagnetic spectrum. So imagine waves of many, many different wavelengths, from very long wavelengths to very, very short wavelengths. At long wavelengths, that's what's used for radio transmissions, shortwave. In your microwave oven, you use slightly shorter wavelength electromagnetic radiation. Then you move into infrared radiation. And actually, visible light forms a relatively narrow band here in the electromagnetic spectrum. And once you get to even shorter wavelengths, you're into the ultraviolet and then into X-rays, which everyone's familiar with from medicine, and then into gamma rays, which is a very short wavelength electromagnetic radiation that comes from radioactive decay and so on. So that's what light is, and that was one of the triumphs of Maxwell, was to show where it fitted into this whole spectrum of all these different kinds of electromagnetic radiation, as we call it in total. Now, one of the features of white light, now you've all seen rainbows. White light is actually a combination of all of the different colors of the rainbow, and with something like a prism, you can actually prove that, and this is one thing that Newton did. You can actually use a prism to separate out the different colors within the spectrum of white light and produce a nice rainbow spectral pattern like that. And this is actually something that is going to be used in this demonstration, which we'll see in a moment. Okay, now another very important result coming out of Maxwell's theory of electromagnetism was that when you accelerated a charged particle, it produced electromagnetic waves. It would give off light or something like that, some electromagnetic radiation with some sort of a wavelength. And this is used all over the place. The modern world couldn't exist without this observation. So antennas, for example, require electric charges to accelerate within the antenna and either emit radio waves or absorb radio waves. And I've depicted here another example. This is the synchrotron. This is actually just a cartoon. This is the one being built out in the eastern suburbs. And what that does is to accelerate electrons around a ring. And when particles are traveling in a circle, actually they're accelerating. And synchrotron light, which is going to be used for a lot of medical applications and even some physics experiments, is emitted from these electrons as they move around in the circle. So all I want you to remember is that when an electric charge accelerates, it emits electromagnetic radiation. If it's just moving with a constant speed, it's not emitting electromagnetic radiation, but when it's accelerating, it does. And this will be very, very important for our story. Okay, now one way, the central way it will be important is illustrated by this little diagram. What we have here is some sort of a molecule, which is just, doesn't matter what, it's some sort of a molecule in some typical substance. Your body or the air or the walls in this room or something like that. And what's happening here is that infrared radiation, which is the electromagnetic radiation that had slightly longer wavelength than that of visible light, when electromagnetic radiation of that particular wavelength interacts with molecules, it sets them vibrating. And that's why we talk about infrared as a sort of a heat source. It's because it's particularly efficient in causing the charged particles in the atoms in our bodies or anything to start jiggling about, get more kinetic energy, and therefore get hotter, have a higher temperature. So that's the connection between, this is a very important connection between radiation and heat. So heat is the disordered, and temperature involves a disordered motion of lots of atoms in a substance. And since those atoms contain charged particles like electrons and protons, these charged particles are going to be accelerating, decelerating, doing all sorts of complicated things. And when they do that, they can emit electromagnetic radiation, they can also absorb electromagnetic radiation. There's a two-way process, and there's a transfer of energy between just the kinetic energy of atoms in the gas and the electromagnetic radiation that is either given off or absorbed. Okay, now, as I've said, it's just a common fact of life that everyday objects both emit and absorb electromagnetic radiation, such as light. So, you know, a light bulb gives off light, and the glass on the light bulb partially absorbs that light, not fully, but partially, and it gets very hot. So electromagnetic radiation is just something that is commonly emitted and absorbed. And what's happening is that when the light from the filament in the light bulb is passing through the glass, it's jiggling all the atoms and molecules in the glass around and causing them to move more quickly, and therefore raising the temperature of the glass. Now, there's a certain graph I'm going to be showing over and over again. So what I've plotted here is the wavelength of electromagnetic radiation. Let me just call it light from now on, but we'll understand that we may be talking about infrared or ultraviolet or whatever. We have the wavelength of light here on the horizontal axis. So these are long wavelengths and these are short wavelengths. And on the vertical axis is a measure of how much electromagnetic energy is emitted by an object in light of a certain wavelength. So for example here, if you wanted to know how much energy is emitted by light with wavelengths between 4 and 6, what you have to do is look at how tall this curve is at that point, what value it has. And you'll see that here the peak of the curve is somewhere around 4. So for this particular substance, it's going to be emitting electromagnetic radiation or light with a wavelength of about 4. You can't see it because I've got my stupid arrow over it, but this says microns, millionths of a meter. Okay, and this is a measure of how much light of a given frequency or a given wavelength is given off by an object. And what you notice is that it goes to 0 for very, very small wavelengths. Now, very, very small wavelengths correspond to gamma rays, things that are only really produced by radioactive decay. And what this is saying is that very little energy is actually emitted in the form of gamma rays by an ordinary object. Then when you go to longer wavelengths, and you get to visible light or ultraviolet or something like that, or infrared, more and more radiation is emitted of that particular wavelength. And then also when the wavelength gets really, really long, again, the energy that's emitted in these really long wavelength types of electromagnetic radiation, again, is very, very small. So there's a peak in the middle, and there's very little on the sides. That's a very characteristic behavior of hot bodies. Okay, now, within the class of hot bodies, there is a special one called a blackbody. And this is of particular theoretical significance. It's the one you really have to think of because it's the simplest one. Ordinary objects have all sorts of complicated features to them. And many of these complicated features you really don't want to think about to begin with because they're just too hard. There are too many complications. And so physicists often like to think in terms of idealizations. And the blackbody is one of them. And this is a particularly important one for us. Now, what is a blackbody? It's an idealized object that has two characteristics. If you shine any light on that object, it will literally absorb 100% of that light. That light will then start to jiggle the atoms in the body around, and eventually that light will all be re-emitted, and all of it will be re-emitted. So a blackbody is an idealized object that doesn't reflect any light at all. Anything that shines on it gets absorbed, it gets processed, and then it gets re-emitted. Most objects actually are approximations to blackbodies. They're not exact. So for example here, there were actually two curves, one which was labeled blackbody and one which was quartz, right? Just a common kind of rock. And so what you see is that quartz, it behaves something like a blackbody, but it has some complicated wiggles and gaps and so on, which just has to do with the details of what quartz is and is not really of general interest. So that's why we're going to focus on this idealized thing called the blackbody. And actually a common sort of way to think about a blackbody is to imagine a cavity with a small hole in it. And this little yellow thing that's bouncing around is meant to depict electromagnetic radiation that is entering this hole. And it then bounces around inside the cavity and basically finds it very, very difficult to get out because this hole is very, very small. And therefore this hole represents a perfect absorber. Okay? So in that sense, it fulfills this criterion of being a black body. It absorbs all of the radiation impinging on it. But if the radiation happens to find itself heading in the direction of the hole, it'll go, because it's a hole, it'll leave. So it's also a perfect emitter of electromagnetic radiation. So often, rather than talking about you know, a specific lump of something as a black body, we think of this sort of slightly strange thing, which is a cavity with a small hole in it, and we think of just the electromagnetic radiation coming out of this small hole. And this is our model for a black body. So I'll actually be talking about something called cavity radiation, which is just all of the electromagnetic radiation that is existing inside this cavity, and that's closely connected with the stuff that's actually coming out of this hole. So I'll use black body and cavity radiation kind of interchangeably. Okay, now Nick has some demonstrations that he will show. The first one involves two spheres. One is black and one is white, and the point is that the white sphere reflects a lot of the light that impinges on it, and that's why we see it as white. It's actually reflecting all of the spectrum of the rainbow, whereas this black sphere is more like a black body. That's why it's black, and it's absorbing much more of the light that is impinging on it, and the heat. And so what you're going to see as these two balls light up, if I use this laser I might kill Nick, but I'll try to be careful. What you'll see is the level in these two tubes that are connected to these two balls go down at different rates. So what's happening? So look at this one. This is becoming much, well, I hope you can see it's a little bit shorter than that one. So what's happening is that these two balls are being heated in exactly the same way, but this one is absorbing more of the radiation, and it's getting hotter. Because it's getting hotter, the pressure in the gas, the pressure in the air in this tube is getting stronger, and it's driving the liquid down. And you can see the difference. And this is exactly illustrating that different objects absorb different amounts of light, and black objects absorb more than white objects. Okay, so that's kind of the absorption part of this black body definition. The other part is emission, and what we have here is a cube, and the different faces of this cube have different colors. So this one is what do you call that? Silver? White? Okay, that one's white, and we have black on this side, and inside there's actually a light bulb, which is just a source of heat. This object here is a detector of infrared radiation, and what you see here on the screen is basically a measure of how much infrared radiation is being detected by this object, and no detection is when the arrow is pointing upwards. So at the moment we're looking at the amount of infrared radiation coming off a white surface, and you see that it's about 10, whatever 10 means. It's in some sort of units. And now we'll rotate it to black, and what you see is that with the very same source of light inside that box, a hell of a lot more infrared radiation is being emitted by the black surface compared to the white surface. So it's a much more efficient emitter of radiation, as well as being a much more efficient absorber of radiation. So that's why black is kind of special. All right, it just gobbles everything up, but it also emits everything later on in the form of light. Thank you, Nick. Okay. So black bodies. Now, as I mentioned, most hot objects approximate black bodies in some way, quartz, but also rather more, well, quartz is interesting, but there are other interesting things called stars. And this is the constellation Orion, which is one of my favorites actually. And one thing that astronomers do is to measure the surface temperature of stars, which are light years away. All right, so how do they do this? How can astronomers know that Betelgeuse here has a surface temperature of 3,000 degrees Kelvin? 3,000 degrees above, 2,000 degrees, sorry, above absolute zero. How do they do that? Well, they look at the light that's coming from a star, and they see what kind of a radiation pattern it gives as a function of the wavelength of the emitted light. And Another characteristic of blackbody radiation is that it varies with temperature. So when you heat a body, what happens is that it starts to emit predominantly radiation of shorter and shorter wavelengths. And so that's what these three curves are. These are three different blackbody curves. One is for something that's 4,000 degrees hot, another for about 5,200, and another for 7,000 degrees hot. And what you see happening is, first of all, the hotter object is emitting much more radiation. You see the curve is much higher, but also the peak of the curve is gradually moving to smaller and smaller wavelengths. So it's emitting electromagnetic radiation of higher and higher frequency, in other words. And in terms of visible light, that means going from the red through to the blue. Red light has longer wavelength than blue light. And so, when you look at stars, astronomers determine what sort of curve a particular star has, and from the location of the peak, they can read off what must be the temperature of the star. And if you actually look at the radiation emitted by stars, it is approximately in this kind of a blackbody form. Okay, and so they can determine that Betelgeuse is a red star, and it looks a bit red, and it's relatively cool, 2,000 degrees surface temperature. Whereas Bellatrix over here is much, much hotter, 25,000 degrees, and it's a blue star. It glows mainly in blue light. Okay, so a lot of interesting uses for this business of the radiation given off by hot bodies. Okay, so this is the same graph again, and this is the guy Wien who studied exactly how the peak of this curve varied with temperature. Oh, and so another example of this is if you just take a lump of iron and you start to heat it. At first, you put your hands around it and you'll feel the infrared radiation coming off. This is light at relatively long wavelength. Then you heat it a bit more, it goes to a higher temperature, and it begins to glow red. Red is the longest wavelength visible light that we have. You heat it a bit more, and eventually it will become white hot, and then blue hot. And that means it is just taking a journey through all of the electromagnetic spectrum, from red at long wavelength to blue at short wavelength, as you heat it. So, and that's why the peak of this curve is actually going to shorter and shorter wavelengths as you actually heat an object up. Okay, so Wien is the guy who studied this. Okay, and as I've already mentioned, and we'll need to keep focusing on, very little energy is emitted both at long wavelengths and at short wavelengths, and you'll see why this is important in a minute. And what Nick is now going to demonstrate is actually in real time, just to show you that an ordinary object produces a curve that looks very much like this. So what we have is basically just a light bulb, right, in here, and so it's just emitting light, ordinary light coming from a light bulb, and then over here there's a prism, and this prism is dispersing the light into the different frequencies that it has, just like you get a rainbow out of a prism, as Newton showed. And this object is a detector, which is determining how much energy it is receiving in the form of light at various different angles. And Nick will rotate this detector at various different angles compared to this prism. And as you go through the various different angles, you're going to be sampling different parts of the electromagnetic spectrum, because you've got this broad rainbow that is coming out of the prism. And so what you see here is he's scanned it across in angle, and he's produced a curve which is representing the light energy coming from this bulb. And you get a curve that looks very much like this. It disappears at long angles and at short angles and at large angles, and it has a peak in the middle. And now he'll turn up the temperature of the light bulb. Actually, he's turning it down. He's made it cooler and produced another curve. And you see that it is following the same sort of a shape, but less radiation is emitted. The curve is longer, and the peak is a slightly different position, although it's a bit hard to tell. But maybe the temperatures are not too different. And I think you're going to do a third one. Okay, and this one should be cooler yet. Okay. So you see this one has hardly moved, and now I think you can see more convincingly that the peak is kind of shifting in its position. So this is just these guys. So just an ordinary light bulb behaves like this. Thank you. Okay, so notice that this graph is labeled with red star and white star and blue star, and that's just what I was saying before. But if you look at the star and you get this sort of a curve, it's telling you that the surface temperature is fairly low, 4,000 degrees, and it looks red. And whereas this curve here represents a blue star and it's much hotter. Okay, now, so the whole point was to try to do some mathematics and to understand where this curve comes from. You know, you can do all zillions of experiments and verify that every hot object under the sun, for that matter beyond the sun, you know, has a curve that sort of looks like this. But how do we understand that? And the ultraviolet catastrophe was the fact that when the physics of the day was used, the best physics of the day, the best thermodynamics and the best of Maxwell, electromagnetism, this is the prediction. And that this dotted line just keeps going up and up and up and up like this. And so at very, very short wavelengths, an infinite amount of energy should be emitted. So we should all be just blowing up in gamma rays all the time. This was the nonsensical prediction. And this was called the ultraviolet catastrophe, just because ultraviolet is you know, the shortest wavelength band compared to visible light. Okay, so this was the problem. They got this curve, and they should have got that curve. And now I want to just try to explain why classical physics predicted this particular curve. And then I'll tell you what Planck did to fix it up. This is, in order to do this, we have to go back to that slightly dry thing that I was describing called the equipartition theorem. What we've got to do is work out the thermodynamics of all of these electromagnetic waves which exist inside this cavity. So this is my cavity, here's my little hole which is representing the black body. And what I've got inside this cavity is just a whole lot of electromagnetic waves. So the physical picture is this. The atoms in the walls here are composed of electric charges that are jiggling about. These electric charges are absorbing this radiation and they're also emitting the radiation. Eventually, these come into a steady state situation and there's no net flow of energy backwards and forwards. I mean, energy is flowing, but as much is flowing into the walls as is flowing out of the walls. So we say they come into equilibrium. And this is what we use to define the temperature of the radiation. Here we're extending the definition of temperature from something that was applicable to point atoms moving around in a disordered way in a gas to a bunch of waves that exist in some disordered way in a cavity. You see, you have all sorts of waves in a disordered sort of pattern in the cavity, and we can assign a temperature to them because when the waves in the cavity, when the radiation in the cavity comes into a steady state situation with the atoms in the walls, we can then define the temperature of the radiation to be the same as that of the cavity. And the temperature of the cavity we can just measure with a thermometer. Okay, now the other little thing that we need to input is that the waves here inside the cavity have to obey a rule. They have to vanish at the boundaries. I don't want to explain why, but let's just accept that they have to vanish at the boundaries. So what you have is the ability to put many, many different what are called standing waves into this cavity. And the only rule is that the wave has to vanish at the walls. So here what you see, let's look at this one first. This is one wavelength, which is nicely fitting exactly into the length of the cavity. This is half a wavelength. This is 1.5 wavelengths. This is 2 wavelengths. And we just keep fitting more and more and more of these standing waves in the form of electromagnetic radiation into the cavity. And we just use this one rule that the wave has to vanish at the boundaries. Okay? So, we call these standing waves modes, different modes, and they have different wavelengths. This has a shorter wavelength compared to that one. And I've just shown you 4 of them, but actually there are an infinite number. You can just have as many wiggles here as you like. Okay, now, when I talked about the equipartition theorem, I mentioned something called degrees of freedom, which was the 3 independent waves that a particle could move. Here we don't have particles, we have waves. And the equivalent concept is how many different waves can it wave? You know, how many different ways can a wave wave? It's a sort of funny piece of English, but this is sort of the question we're asking. How many different ways can waves exist? And the answer to that is basically, you just have to count how many standing waves you have inside your cavity. So you just have to start just putting waves, half a wavelength, 1 wavelength, 1.5, 2 wavelengths into the cavity, and then just start counting how many of these things you have. And that is going to be the number of degrees of freedom. And this is the number of different ways, if you like, that the electromagnetic radiation can move. It's equivalent to a particle being able to move in 3 different ways. And so the way that Rowley and Gibbs did their calculation was that they said the total energy of the radiation was equal to the number of these modes that you had multiplied by T, multiplied by the temperature, just in the same way as we worked out the energy of a gas. Okay? Now, the ultraviolet catastrophe arises because when you go to shorter and shorter wavelengths, you can fit more and more and more of these modes into the cavity. You can, try to imagine fitting half a wavelength of fairly long wavelength radiation into a cavity. There's only one way to do that. But when you have very, very short wavelength radiation, you start to be able to put in more and more of these standing waves into the cavity. You get more and more of these modes. And each of these different modes contributes to the total energy of the radiation. And each of them is proportional to the temperature. So basically what you end up with is an infinite amount of energy as the wavelength tends to 0, because you can just start fitting an infinite number of waves of arbitrarily short wavelength into this cavity. And this is actually called the ultraviolet catastrophe. Here is just some my attempt to illustrate this a little bit better. Here is 1 wavelength fitted into the cavity. Here is 2 wavelengths. Here is 3 wavelengths. And if you ask the question, how many waves are there, how many modes are there that have wavelength between, say, 1 and 0.997? I'm going to choose a wavelength interval of 0.003. This is in some arbitrary units. The answer here is there's just 1. You can fit 1 wavelength in. The next one you're allowed to fit in has a wavelength of a half, and that one and a half is 0.5. It's not between these 2 numbers. So there's only 1 wave that has, 1 mode that has a wavelength in this interval. If we take the same interval of 0.003 but reduce the wavelengths we're considering, so let's look at between 0.047 and 0.050, now actually there are 2. You can figure it out fairly easily. There are 2 modes that can be fitted in to that interval. It's the same interval as we had here, 0.003, but now there are 2 modes that fit in to the cavity, obeying this rule that the wave has to vanish at the boundary. And if you go to even shorter wavelengths, here we're talking about 1/50th to 1/58th of the width of to the length of this cavity. Actually, now you can work out that you can fit that there are actually 9 modes that exist in this interval, in this particular interval, 0.017 to 0.02 of wavelength, which is again a 0.003 interval. So as you get to shorter and shorter wavelengths, you just have more and more of these modes, and you just have to count them. And so basically, this curve had this disastrous catastrophic behavior because the number of modes was increasing to infinity. For example, suppose this interval here represents 0.003. Then when we had long wavelengths, we could just fit 1 in, and so this curve isn't very high. When we went to wavelengths more like a 20th, we could fit 2 in, and so the curve was a little bit higher. And then we went to wavelengths of about a 50th, we could fit 9 in, and so the curve is even higher. And then as we go to shorter and shorter wavelengths, this curve just keeps rising and rising and rising, because we just get more and more of these very, very short wavelength waves inside this cavity. So this is exactly why classical physics predicts this catastrophic behavior, why we should all just blow up in a burst of gamma rays, because gamma rays have very, very short wavelengths, and there are many, many, many different ways to fit gamma radiation inside a cavity. This was basically why. It was kind of a democracy. You have to treat all of these different modes equally. This was the rule of classical physics, and it led to nonsense. Okay, so Max Planck, in the year 1900, really tried to understand what was going on. He won the Nobel Prize for this work eventually, and celebrated on postage stamps and the like. And basically, he just had a guess. He wanted to derive that blackbody curve, the one that went up and then went down again. And first of all, he took the works of Rayleigh and Jeans, he studied them very carefully, and he couldn't find anything wrong with their reasoning. Their reasoning was perfect, therefore there had to be something wrong about their assumptions. And what Planck's genius was to guess what was wrong and to guess the correct replacement for a wrong principle. And so what he had to do, well, what he knew he had to do was somehow make these very short wavelength modes unimportant. They were becoming infinitely important in the classical approach. And they had to become very, very unimportant because this curve had to go down to zero. And so basically what he introduced was a cost. There was an energy cost. If you wanted to produce electromagnetic radiation of very, very small wavelength inside your cavity, you had to pay an energy cost to do that. And that cost went up as the wavelength went down. And because of this energy price that you have to pay, which is actually encompassed by this famous energy quantum formula, you take the frequency of your light, you multiply by a new fundamental constant of nature, which is named after Planck, and that tells you the energy cost that you need in order to be able to have light at that particular frequency inside the cavity. Or this is the formula in terms of wavelength. And basically, as wavelength goes down, the energy quantum goes up. There's a higher price to pay for having very short wavelength radiation inside your cavity. And I mean, one thing that I really like about this is that nobody told Planck that this is what he had to do. There was no rule. He couldn't go to a textbook. He couldn't go to the treatise of Maxwell. He couldn't go to any book to find out what he had to do to understand this radiation. He had to take a stab in the dark, so to speak. He had to have an inspired guess. And one of the things that bothers me, I suppose, in the view that many people have about science, is that they see this as sort of very cold, inhuman process where you sit down and you're really, really logical the whole time. And actually, sometimes you are, and sometimes it's a very good thing to be. But many of the very greatest advances in science come not from cold, clear, deductive logic. They come from wild guesswork, just inspired guesswork, just taking a stab in the dark. And some people get very, very lucky, and you know, they make great advances, they become very famous, and more importantly, the rest of the world then understands something they didn't understand before. And Planck's guess was just like that. There was no precedent for it. Just introduced a new principle. There's this energy cost, the quantum. Okay? So, I don't know, one of the things I'm inspired by in science is that it's a very, very creative activity. It's not just sitting down and crunching numbers and doing mathematics. Sometimes you just have to have a wild idea. Not all wild ideas are good, very few of them are good, but occasionally one is really brilliant. Okay. Okay, so this just basically summarizes what I said. Small wavelength modes, the ones that are troubling, the ones that lead to this ultraviolet catastrophe, just get harder and harder to produce because you have to have at least one quantum's worth of energy at that wavelength to produce that radiation. And the quantum, this price, just goes up as the wavelength goes down, and eventually you can't afford it. You know, you only have $100,000, you can't afford to buy a house anymore. Okay, so you've got no house. Literally no house. here's another view of it. This is the classical disastrous prediction. Here is reality. And by the way, Planck didn't only get it approximately right, he got it completely right. Okay? He just had this bizarre guess, and he got the formula exactly right. So what you see here is the quantum energy cost kicking in. At very long wavelengths, the classical result was actually fine. If we were to take this out to 4,000, 5,000, 6,000, here it's nanometers, we would find that this Planck curve, as it's now called, and the classical curve actually agree very well. It's at the short wavelength end of things that everything went awry. And that's because you had to take the energy cost of the quantum into account. And that's what it does. It just brings this curve down into the one that really exists. And down here, when you get to infinitely small wavelengths, actually you have to pay an infinite cost. If you want to buy the planet, you can't do it. You just need an almost infinite amount of money to do that. And if you want to produce a whole bunch of gamma rays in your toaster, you can't, because you can't afford it. There's a too big an energy price to pay. Okay, now, our friend Max Planck, always looks like a very stern character to me. And there, he didn't want to be a revolutionary. He was kind of a reluctant revolutionary. And one way in which he was conservative, he wanted, although he made this inspired guess, he wanted to make the minimal inspired guess. He wanted to assume just as much, he wanted to assume as small a new principle as he could get away with in order to understand the radiation of hot bodies. So he was basically a conservative, but he was forced to be a bit radical by reality, by having to agree with experiment. And so actually the conservatism here was the following. What he was considering really was the process by which the radiation inside the cavity was absorbed by the walls and then re-emitted by the walls. And he took that to be a discontinuous process, that you had to do it in these quantum lumps. So for a given wavelength, there was a certain quantum, and one quantum would be emitted or absorbed, or 2 quanta, or 3 quanta, or a certain integral number of quanta. But the quantum came in the interaction between the atoms and the radiation. It was kind of a fussy sort of point to make. What he didn't imagine was true was that the electromagnetic radiation itself existed in the form of discrete lumps with energies given by his famous formula involving Planck's constant. You see, one way to understand this energy cost is not to think of the radiation in the cavity as being a bunch of waves, but to now think of it as a bunch of particles. And we call these particles today photons, particles of light. They really exist. If you think of light not as waves but as particles, then what happens is that Planck's formula tells you that when you have very, very short wavelength light, the energy of one light particle of that wavelength is really high. And the way you emit and absorb that radiation has to be in these particulate lumps, because the radiation exists in the form of particles. You don't have any choice. Planck didn't want to make that step. He didn't want to actually resign himself to the fact that the electromagnetic radiation most probably also existed in the form of lumps or quanta or what we now call particles. He tried to be as conservative as possible, and he just said that the wall radiation energy exchange process was discontinuous, but the radiation itself was sort of perfectly classical. And actually, Einstein's contribution in 1905, which I'll talk about next year, which involves another reasonably mundane process, but with very profound implications, the photoelectric effect. Einstein's contribution was actually to basically prove that the radiation itself had to exist in the form of particles. There wasn't enough to just say that when radiation hit a bunch of atoms in a wall, then the exchange process was discontinuous. Actually, the radiation itself was discontinuous. Okay, and so Einstein, just 5 years after Planck, was the one who took an even more radical step, if you like, and said that no, we have to come to terms with the fact that electromagnetic radiation, which we've been thinking of very profitably as a wave, actually, in many respects, behaves like a bunch of particles, just like the atoms in a gas. It's like hydrogen atoms in a gas, the oxygen atoms in this room. Electromagnetic radiation apparently behaves like a bunch of particles. On the other hand, we know in many ways that it also behaves like waves. Okay, it was sensible to think about waves. There was a lot of evidence for that. And anyway, this begins the whole kind of headache of quantum mechanics and how you put particle notions and wave notions together. And I'll talk about that more next year after introducing Einstein's momentous contribution. But before we go, I just wanted to show you a nice picture. This looks like an Easter egg. I think it's meant to be our universe. I think what this is meant to be is a depiction of the sky, a sphere around the Earth. What this actually depicts is the most perfect blackbody ever found. I kept emphasizing that all objects approximate blackbodies, and this funny construction, a hole in a cavity, is somehow a good model for a blackbody. What actually is the most perfect blackbody ever found? And the answer, if I wanted to be really dramatic, is to just say our universe. Our universe is a blackbody. Actually, it's a component of it. There's something called the cosmic microwave background radiation. This is electromagnetic radiation, light, that is left over from a very early stage in the evolution of the Big Bang universe. You know, the universe began as a very small and hot and dense object and has been expanding and cooling ever since. And at a certain point, the universe became transparent. And at that point, whatever light was flying around suddenly could fly forever. And it's still flying today. And it's called the cosmic microwave background. And what this actually depicts is the sky around the Earth and the cosmic microwave background radiation, which is the most perfect blackbody ever discovered, as far as I know. And actually, these hot spots and cold spots represent minute departures from perfectness, if you like, perfection. So, a given blackbody curve has a certain temperature, okay, 2,000 degrees or whatever. Actually, here it's more like 2.7 degrees. So what instruments have done, like the WMAP satellite that announced results last year, is it looks at a certain point in the sky and it measures the temperature of the cosmic microwave background radiation, this relic from the very early universe. It just measures the temperature in a certain direction. Then it measures the temperature in that direction. Then it measures the temperature in that direction, and so on, over the whole sky. In each particular direction, it sees a perfect blackbody curve with a certain temperature, capital T. In another point, again, another perfect blackbody with almost the same temperature, capital T. Almost the same temperature. Now the level of precision is fantastic, and actually they can begin to see what are called temperature anisotropies in the jargon. These are slight variations in the temperature or the blackbody radiation coming from the universe in different directions. And so these hot spots and cold spots, I guess that's hot and I guess that's cold, represent these minute fluctuations, 1 part in 100,000 in the temperature of this most perfect blackbody that we know, which is actually the radiation filling the entire universe. So that's kind of interesting. Why there's sort of darkness over here like this is a planet, actually I don't know. I think that's poetic license. Okay, so quantum mechanics, which is one of the cornerstones of physics, was born in this way in 1900 through the agency of Planck. It really became a mature theory in around 1925, and it's now called quantum mechanics. Next year I'll talk about Einstein's contribution, as I said. Actually next year I'm going to try to do something I hope rather interesting, which is to talk more about the strangeness of quantum mechanics. We've only really just touched upon it here. Here we were really concerned with nitty-gritty things to do with the radiation emitted by hot bodies. But actually, when you look at the full implications of quantum mechanics, they're rather mind-boggling. And so next year I actually want to spend a lot of time not talking about nitty-gritty things, but talking about what quantum mechanics is saying, and how humanity has sort of struggled to understand it over the last 80 years, and how I think that now maybe almost, more than a century after its birth, if you take its birth at 1900, we perhaps are finally starting to understand the meaning of the quantum properly. So see you next year, and thank you.
Well, I think in view of the hour, we've got giving birth to the quantum there took a lot longer than perhaps we anticipated, but I'm sure we could take a couple of quick questions before we let you go back out into the universe. Yes, up the back there.
So, the many-universe theory of quantum mechanics, which obviously you'll talk about maybe next year or something,
Yeah.
how do you feel personally? It's almost like a concept that's almost impossible to believe, but do you feel that is a concept that's justified in all its understanding?
Yeah, you've asked the perfect question. I've been dragged kicking and screaming to the view that it's to be taken seriously. I still don't like it, but if you take quantum mechanics seriously, then there's many worlds. I don't know if I should introduce it now. I probably shouldn't, but maybe many of you have heard of this thing called the many worlds interpretation, which many people find rather distasteful, and certainly I did and sort of do find distasteful, but it's really not a question of what we like or what we don't like, but what our theories say. And if you take quantum mechanics seriously, then I think you also have to take the many worlds interpretation seriously. Let me put it another way. I don't think anyone has done an experiment which has falsified that view of the world. Maybe it's not the correct view of the world, and maybe I even hope it's not the correct view of the world, but no one has yet falsified it. And I think it's very important to try to do that. Well, David, challenge.
I think if we're going to start talking about many world theories, we'll be needing to serve breakfast at the end of the July lecture. I think we'll take one further question from right up at the very back there.
Just referring to the point you made on the human question, you made the point that so many advances came out of this sort of chaotic guesswork or pop luck, or we call it creativity. Do you have an explanation why that might be so? Is there some kind of pattern that we don't see, or is it just a random thing that strikes particular individuals that are either called geniuses?
Well, I don't know. I think creativity is a very precious thing. I don't know where it comes from. Maybe some people just feel less constrained in their thinking, and move off in all sorts of tangents, and occasionally have a very bright idea. I don't know. Why are some musicians, so creative and write such inventive melodies, and others, not so? Who knows? I think it's the same kind of phenomenon.
Well, I think on that note, we can say we're fortunate of all the worlds that we have the creative Professor Ray Volkas in ours, who can talk about these topics with some profound insight. So these are, in fact, the 4 July lectures we've got lined up for you in the International Year of Physics 2005, and I'll invite you all to come back then. I should, just before we adjourn, after last week's lecture there was a couple of items left behind in the theatre. If you recognise any of these, please come and collect them. And also someone may have made off with a set of notes that were in a blue plastic bag very similar to this. So if you've got an unfamiliar blue plastic bag in your possession, there's someone who's anxious to get it back. And I should say, the July lecture program only functions, and the only thing that inspires us to get up here year after year and give these lectures is an excellent audience. And I know Melbourne has a lot to offer on a Friday night. There's the football, there's the casino, there are the restaurants, the cafes and the bars, and yet, and there's the shocking weather, and yet you continue to come. So that's worth taking a photo of the radiation emitting, because I like to show our Dean that Melbourne has a great thirst for physics. So thank you very much. Thank you for coming, and thank you again.